Okay, in our last video, we talked about the electric potential difference across components in a circuit, which was one of the quantities you measured in the light bulb lab. Today, we're going to talk about current, which is the other quantity you measured in the light bulb lab. And I have a link here to a video that I think does a nice job of talking about current and electric potential difference in circuits in general. So I strongly encourage you to watch that on your own. But in the meantime, let's go ahead and let's define current, because you measured it, but we never really defined it. So current is simply the rate at which charge flows past a point in a circuit. And there's a couple common misconceptions regarding current. Okay, the first common misconception is that the battery supplies the electrons. We talked about this a little bit in the last video, but the battery does not supply electrons. The electrons already exist in the wires. So that's why we have this little picture here. Okay, so we have a picture of a wire. We kind of blow it up a little bit so you can see it. And these red arrows represent the electrons. And we know in a conductor, we have a lot of free-moving electrons, free-flowing electrons. And these electrons are already moving before this wire is hooked up to a battery. It's just that they are all moving in random directions, so we don't get any sustained current. Okay, so the wire has lots of free electrons already. The battery doesn't need to supply any. It's just that the wire is random. All the electrons are moving all over the place, so we don't get any kind of a flow. Okay. The second most common misconception is that current is like a velocity. Current is not a velocity. And the problem is this idea of rate. Okay, so it's the rate at which charge flows past a point. But it's not a velocity, so we're not determining how fast they go past that point. It's more similar to a count. So how many electrons are flowing past a point in a given amount of time? Okay, similar to a count, flowing past in a given time. And you can imagine that electrons are really, really small, really, really small. So it's pretty easy to get a large current because we can get lots of them. There's so many in this cross-sectional area, right? There's so many electrons in this cross-sectional area that we can get lots of them to go across, okay? The other misconception is that electrons actually move slowly across the wire. People think they move fast, but electrons move very slowly. It's just that there's so many of them, okay? So we don't need the electrons to move fast to get a big current. We just need lots of them to move. And that's pretty easy to do because there are so many of them. And the reason they move so slow is because there's so much in the way. Right? You can think about all the atoms. The atoms are relatively big compared to just the single electrons. So the electron is going on its merry way, but then it bumps into an atom and it gets diverted from its path. So a lot of that is what's happening in the wire. So if we look here, this is a wire that has a current flowing through it. So we've got our positive just charge that's moving to the right, and they're all moving together, but there's always something that gets stuck in the way. So it's kind of a zigzaggy path. So the electrons, the total velocity ends up being pretty small when you look at it, okay? But there's so many of them that we can still get a big current. So let's go ahead and talk about our units. So we said that current is a charge, right? Basically count how many electrons or how much charge is moving past a point divided by time. So our units, we remember from our last notes that we're going to measure charge in coulombs, and as usual, we're going to measure time in seconds. So our units for current are going to be coulombs per second, which of course we have to give a special name to. We call it an ampere or an amp or just capital A. Any of those will do for units for current. And those are the units that you used in our light bulb lab. Now, I know we mentioned a little bit about this next part, that electrons and conventional current, but I want to make sure we understand. We know, we're certain, that the electrons are what flows through a wire. We know that. We talked about that. Protons don't move, right? They're pretty much stuck. So we know that electrons are flowing through the wire. But we saw in the light bulb lab that the direction of the flow doesn't matter, right? If we hook up the light bulb one side to the positive and one side to the negative, it lights up. If we turn the light bulb then, or we turn the battery and hook up the battery to the opposite side of the light bulb doesn't care. It lights up just fine. So the direction of the flow doesn't matter. It turns out that the sign of what's flowing doesn't matter either. It can be positive or negative. And this is the source of the issue with what we see and what we're going to call conventional current. So if you go back far enough in time where people didn't understand electrons and protons and what was making up the different atoms, Ben Franklin figured out what electricity really was and what current really was, and it's just the flow of some charged object. And he knew that there were positive charges and negative charges, but he couldn't tell one from the other. So he said, you know what? I'm going to take a guess. And he had a 50-50 shot at being right. I'm going to guess, he said, that it's the positive thing that's flowing. He took a shot. He had a 50-50 chance. He got it wrong. It turns out that we know now that it's the negative electron that's flowing. But the problem is that all the books had already been written. And they had already assumed, and a lot of the people had already assumed, that Ben Franklin was right and that it was the positive thing flowing. He got it wrong, and nobody wanted to change it. So we are still stuck with this idea of conventional current, and conventional current simply means that there's a flow of some positive object or some positive charge. Even though we know that it's the electron that's moving. So we are going to always assume conventional current from now on. We will always use conventional current. And that's the flow of a positive charge. So that is why, okay, when we look at a battery, and this is why, when we look at a battery and we say, oh, look, we've got the positive side here, we've got the negative side here, the current flows from the positive to the negative. Well, think about that. What that's saying, if we were assuming that the electrons were flowing, why would the electrons ever leave this positive side of the battery? They'd be very happy there. The electrons would always want to stay there. But by saying that we have the current flowing from the positive side to the negative side, that means that it must be a positive charge that's moving. It's got to be the positive charge, because the positive charge would never stay here by this positive side of the battery. They'd want to get out. They'd want to go to the negative side. So just on the basis of how we've been drawing everything and how we've been talking about it, we know that we're going to be using conventional current. So let me get rid of this. We don't need this. Okay. And then let's go ahead and let's talk about resistance, because resistance is something that we've kind of noticed, but we haven't talked about. So resistance is simply a hindrance to the flow of charge. Resistance discourages, I hope I spelled that right, discourages the movement of charge. Okay, some misconceptions. Resistance does not destroy charge. We cannot destroy charge. We can't take an electron and poof, make it go away, or a proton and poof, make it go away. Okay, it does not slow the charge. But it does allow less charge to pass. To pass a point in a given time. So let's use another analogy. And let's take a look at our other picture to the right here. And what we've got is we've got a water pipe. And there's a turbine in there. And the amount of water leaving the turbine has to equal the amount entering. This is similar to the flow of electrons. Whatever electrons we have coming into the light bulb has to be the same number of electrons that are leaving it. They're just leaving with less energy. So we can't lose electrons, just like we can't lose water. Now, let's keep going with this analogy. This pipe will eventually get really dirty and grimy from the water, and it'll build up kind of scale on the wall. Well, in that case, not as much water will be able to flow through the pipe. So the resistance has increased because the pipe got smaller. Okay, so we still have the water flowing, but not as much will go by in a given period of time. Same thing with the wires here. If we increase the resistance, the electrons will still move through, but we won't have as many moving through. So the current will decrease. Now we don't have to worry too much about resistance in a wire. The only thing I would like you to kind of keep in mind is that the resistance is pretty much determined by a couple things. It's determined by the material of the wire, right? A better conductor will have less resistance. So something like copper obviously is going to be much better than something like plastic or glass, okay? The resistance is also determined by the cross-sectional area of the wire. So similar with our analogy with the water pipe, a bigger wire will have less resistance, just like a bigger water pipe will have less resistance. It's also determined by the length of the wire. So a really long wire will have more resistance. And it can also be determined by the temperature of the wire as well. We won't have to worry about that. Now, for our purposes, we're going to assume that all wires have a resistance of 0. Okay. Last thing that I want to add in here are the units we're going to use to measure resistance. We use ohms, OHMS, to measure resistance. But you can't use O. You can't use O. You can't say, oh, something is 4 ohms. Because if you said it was 4 ohms, what does that look like? That just looks like the number 40. So we don't use O to stand for ohms. So let's get rid of this. We use an omega. And it kind of looks like a circle with 2 horizontal legs. This omega. But we would just say something like 40 ohms means there's a resistance of 40 ohms, okay? We'll talk about, and when we get a little further along in our next notes, what we're going to do with that value. All right, let's talk about what we saw in some of our circuits, specifically our parallel circuits. And let's look and see what happens at a junction. So we've seen some junctions, and if you look ahead a little bit, this is what I mean by a junction. So this right here is a junction, 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 junction. It's just a location where wires come together. Okay, so a junction is just a location where wires come together. And what we not want to realize is that all current into a junction must also leave the junction and have current collecting. So what that looks like is that the input current, so let's just take this first junction where we've got 1 input and 2 outputs. The current coming in has to equal the currents coming out. So for instance, if we said, oh, we've got 5 amps of current coming in, and I know that through this leg there's 4 amps of current, that means that through this leg I have to have 1 amp of current. I have to. It has to add up to what was coming in. So this is a single input and 2 kind of output junctions. We could also have 2 inputs like we do on this second picture and just 1 output. They could be combining. So that's kind of like what we see right here. This is kind of combining on the out. So we've got 2 kind of coming into just 1. Here we have 1 breaking off into 2. Right here we have 2 combining into just 1. So in that case, let's see if I can get this to work. There we go. In that case, for instance, let's say we have a 2 amp current in this top one and say a 6 amp current in this bottom leg. That means our output current has to be 8 amps because we have to have an equal amount at the junction. Okay. Now the question becomes then, well, wait, why aren't they equal? Why don't I have the same amount of current, right? Why isn't this 2.5 amps and this 2.5 amps? Why is that? Now, what we're going to see, and this is just kind of a preview for what we're going to talk about when we get to Ohm's Law in our next notes, but what we're going to see is that the amount of current through each branch is determined by the resistance in the branch. So the amount of current in each branch is determined by the resistance in that branch. And just like when you're driving into the city, if you see that there's two roads you can take, right, road A and road B, which one are you going to take if you get a good view? You're going to take the one with a lot less resistance. So more resistance is going to result in less current. So looking at the picture above here, I can see that since there's 5 amps coming in, I can see that this branch right here must have a higher resistance because there's 4 amps going through here. So the current, since this is a greater current, there must be less resistance in that branch of the circuit, okay? So let's take a look and let's see what this means for us in our series circuit, okay? So in our series circuit, we saw, for instance, that maybe we measured a current of 5 amps coming from the battery. Well, what that means, since this is a series circuit, is that there must be 5 amps through each of these components. The currents through the components are all the same as the current from the battery. So I'm going to make a little separation there. So the currents through each component are the same as the current from the battery. And that's because there's no junctions, right? When you look at this, you see there's no junctions. We can't split off any current, and you can't lose current. You can't destroy charge. So we can't lose any current. So that means that the current through all of those components absolutely has to be the same. This is going to be different when we look at a parallel circuit. So let's look at a parallel circuit, and let's just assume, and I'm just making these numbers up, let's just assume that we've got 9 amps coming from the battery. That means we've got 9 amps here and there. And that means if each of these components are the same resistance, that means then that we would have 3 amps going through each of these branches. And that back here, they would have to add all up to, oh, why did I put 6? I don't know. They would have to add up to 9 amps. Now right here, and this is why I put 6, because I was thinking ahead, I guess. Right here, what we've got is we've got 3 amps coming from here. We've got 3 amps coming from here. So at that location, we actually would have 6 amps of current. Okay? Now, why are they all equal? They are all equal because we're assuming that the components are all the same. Okay? So first, let's talk about how the currents through the branches add to the total current from the battery. Right? So we have 3 amps through this branch, 3 amps through the next branch, 3 amps through the next branch. That all adds up to 9 total amps. That's the current that's supplied by the battery. Now the current through each of these components is only equal because the components are the same. So the currents through each branch are equal because the 3 resistances are equal. What does that mean? It's just the same component. Or same light bulbs. Could we have a different situation? Absolutely. So let's say we take our battery and we still have a 9 amp current, but we have 3 components that are different. So if we still have 9 amps here, maybe through this branch I've only got 2 amps, and maybe through this branch I've only got 1 amp. Well, you tell me, and I can't hear you, so that's up to you whether you speak it out loud, but you tell me, what does the current through that last branch have to be? Well, you got it right. 6 amps. So that means then that right here, right, that's still 6 amps, but right here, what is the current right there? Well, that's the 6 amps plus the 1 amp, so that's 7 amps. And then the current right here in this wire, well, that's the 7 amps plus the 2 amps. That must be the 9 amps. So we haven't lost any current. This last part of the notes is meant to be done as part of a demo. So if you were in class, you would see that I would have a wire hooked up to an outlet, and that I would be using some pretty large bulbs to show you how the current changes when we have a different number of components in the circuit, or when we have a different setup for the circuit, series versus parallel. So for right now, until I figure out how to get that and make that as part of the video, do some kind of split screen, I'm just going to say that you'll just have to trust me. So what we've got here is we're going to look at the difference between a single bulb connected to a power source, battery, and two bulbs connected in series with the power source. And what we're going to say is that the battery, this is going to be the plus side, and this is going to be the minus side of the battery. And that at this point in this circuit, we're going to call this 100% bright. We're going to say this is as bright as it gets. And we know that we've got our current going like this, so we're going to call this I1. We don't know the voltage of the battery, we don't care. We just know we've got some current going through, and that current results in a battery that's as bright as it's going to get. Okay. Now we're going to look at a second situation where we've still got our battery hooked up the same way, but now I've got two bulbs in series. And what you would see if you were in class seeing the demo, you would see that these are significantly less bright. We'll call it maybe 50% as bright as when we had just one single bulb in series. We still have current, but we're going to call this I2. And what you saw in the light bulb lab, and what we're going to confirm, is that the current through the first circuit is significantly larger than the current through the second circuit. And that is what causes the brightness to decrease. This is much dimmer. Our current decreased. Now, why did it decrease? It decreased because we have more resistance in our circuit. So more resistance in the circuit with the same electric potential difference means a less current. Less current means less bright for the battery because it has less energy to convert to light or heat energy. Okay. Now, the next circuit we're going to look at is going to be the parallel setup. So we still have the same kind of initial setup where we still have our battery. Okay. This bulb is still what we're going to call our 100% bright. And the current going through is the same as it was above. It's still I1. Now, in this circuit, we've got two bulbs in parallel. So what you would see, and this is, you're just taking this on faith and based on what you saw in the light bulb lab, that this bulb is exactly the same brightness as this bulb, which is exactly the same brightness as our original bulb when there was only one bulb in the circuit. So let's go ahead and let's see what this means from current. So our current is coming through here, and let's just call this I3. Some of that current is going through this bulb. Let's call this I4. And some of this current is coming through this bulb. So let's call that I5. Now, if this bulb is as bright as this bulb, that means I5, the current through this bulb, has to be equal to the current through I1. Same thing for I4. This current through this bulb has to be the same as this current through I1. Well, that means that I1 must be less than I3, which is the total current that the battery is supplying, right? So the current that the battery is supplying is increasing in this circuit because this could basically be I1, right? So all the current's going through here, from here. So we've got all this current through here, all this current through here. These have to add to I3. So we could write that and say, well, I3 has to equal I4 plus I5. So that's a lot of current. So by hooking up that second bulb in parallel, we have increased the current that we're delivering. Compare that to when we had the bulbs in series. We decreased the current. Well, that's interesting. So we put another bulb here. We said the resistance increased, so the current decreased. Here, we know the current increased. So the resistance that the battery sees must have decreased. And in fact, that's what happened. Now, this is really confusing, and I get this, because you're thinking, wait a minute, how could the resistance that the battery sees have decreased when you added a resistor? But I didn't just add a resistor or a light bulb. I added a second path. So I want you to compare this to taking a trip down into the city. If there's only one road, right, that's it, one road, one path, one lane into the city, you're going to get a lot of cars on there. The number of cars represents the resistance in the circuit. There's going to be a lot of cars because there's nothing you can do. There's a lot of cars. Say there's 8,000 cars. That's the resistance, 8,000 cars. But now I go ahead and I add a second path. Well, now with that second path, the resistance is going to decrease because a lot of those cars could go down that second path. So even though I've added some resistance, maybe I add another 1,000 cars, I still have decreased the total resistance because I've added that second path. Okay, so just because I've added a resistor doesn't mean the resistance increases. It's because I added it in parallel. Okay? These next two circuits are called combo circuits. So these are combination circuits. Maybe you can hear my dog barking in the background. Okay, dog's finished barking. So similar setup where we've still got our positive and negative battery. We're going to call this current, we're going to call this I6. That means this is I6, but we see when it gets to this junction right here, it splits off. So we're going to call this I7 and this I8. Now let's talk about the brightness of the batteries, the brightness of the bulbs. And let's look at our resistance. So we know that these bulbs are going to add resistance to the circuit because we've got to go through this and we have to at least go through that as well. So the current, you have to go through this resistor and then this. So this is going to be more resistance than, say, what we saw up here in this circuit. So this bulb is not going to be as bright. It's not going to be as dim as when we had two just perfectly in series, but this one's not going to be as bright. So maybe we get this as somewhere around 75% as bright. Well, then the current has to decrease from I6 to I7 and I8 because we know that I6 equals I7 plus I8. So these guys here have to be even dimmer. So this might be, I don't know, 37%, and we don't need the numbers, but just to give you an idea, it's much dimmer, okay? So we know that I6 is less than I1, which was our current when we just had one single bulb attached with the battery. Well, this is going to be different. This circuit here is going to be much different to the circuit we see on the right. So same idea, same battery. But look at this one of the circuits. So this is a parallel, this is kind of a series with a little combo parallel. This is more a parallel with a little combo series. So one of the circuits I can make is this right here, where I go just from the battery to light bulb C. Because of that, I'm going to see that this light bulb is actually 100% bright, right? It's as bright as it's going to get. And let's go ahead and label some currents. So let's call this, where did we leave off? I don't know even. So we'll call this I9. Then the current here through each of these, and that's a little large, let's just call it I10. And let's call this I11. Okay? Well, what we're going to see is that I9 is going to be greater than I1, right? Because I've got whatever current I had flowing through this circuit here, right, is the same current that's flowing through here. So I11 is going to be equal to basically I1. So we could write that. So let's go ahead here and let's say I11 is basically going to be equal to I1. But then this current I10 is going to be less than that because we've got these two components in series. So while I9 is greater than I1, we know that I9 is equal to I10 plus I11. So these guys here are going to be less bright. They're going to be like 50% as bright as the full one. Okay, so this was a lot of information, and we're going to get some practice in this and finding these out, but just to give you some relative idea of how these work, right? The way that a circuit is hooked up is very much going to determine the brightness of the bulbs, and the brightness of the bulbs is always determined by the amount of current through them. Okay, these notes have been long enough. I'm going to stop it there. We're going to have some more notes in a couple of days, and we will visit this and try a bunch of problems that are kind of based on these ideas. All right, have a good day.